I'm glad I can get you back on, or I can get you on. Kind of be going back and forth. It's been like 8 months now. Time really flies.
Yeah, right. And my schedule just gets so busy, and it fills up just for so many weeks in advance as well. It's like something
Mm.
that anyway. I I mean, it's not like I'm actually, I don't have any important titles or anything at the moment, so I shouldn't really be that busy. I'm just a regular faculty member. So, but anyway, I guess
Yeah,
I
you
should
could.
stop
I have a
volunteering.
theory, and you could tell me
Mm.
if it's right or not.
Yeah.
So from some of the people I've talked to, and I was talking to him during the school year, and I wanted to get him on the podcast, and so I asked them if they wanted to come on, and everyone kind of offloaded it to the summer. They were like,
Mhm.
"Oh, like in June or in May, I'll
Yep.
have so much more time. Like that would be a good time to do it." But then as soon as that rolled around, they would either like stop responding to me, or they would be like, "Hey, like I need to cancel. Like I got too much going on. I'm really sorry." And so I had a theory that a lot of academics during the school year tend to offload things to the summer
That's
because
right.
like I
Yep.
kind of did that as a student too. And you'll be like, I'll have so much time during the summer. I don't have to teach classes. But then you end up offloading so much to the summer that your summer fills up just as much as your school year.
Oh, that's absolutely right. So yeah, I've long had this opinion that despite the fact that we're supposed to lead these very thoughtful lives, we're essentially amoebas. So like we're so deadline driven that it's just all immediate stimulus and response to a deadline, and we do things when at the last minute. Not, I mean, partly because I guess a lot of us will procrastinate anyway. But also I'm usually busy doing other things until the last minute, and then I switch to this thing because it has to be done right now, and then I go on to the next thing that has to be done, in a few hours' time. Yeah, it's not a very good way to live, but I think it does seem to be very much a pattern. So, and there's an interesting story about this. So, a few years ago, the National Science Foundation switched from having deadlines for most of its grants. So there would be a specific, 5 p.m. on this day, and so everybody would turn in their proposals, in the basically 2 days up to about the latest one I turned in was literally 5 minutes before that deadline, that was a very scary experience. Anyway,
Yeah.
um, and so a few years ago they did away with the deadlines and just said there's no due date, just send us the proposal whenever it's ready. The number of submissions they received plummeted, and it's because we're all driven by deadlines, and without a deadline we can't finish things. We're kind of conditioned to it now. It's anyway.
That's an amazing wide scale study of human psychology. And I hope somebody wrote a paper on that phenomenon
Oh, I mean, they
or
did it
like that
very so.
specific instance.
It was the Astro division, I think, that pioneered it because I know my wife's in astronomy, and I know that they did it with them before they did it in Earth Science. So yeah, it was very deliberate, and I think they did. I don't know if they ever wrote it up or not, but they certainly had all the data and would talk about it. So anyway,
Yeah. I mean, if you think about it, I mean, that's how it's how we're trained, at least. Like, I can't speak to school in any other countries, but school in the US is very deadline driven. Like,
right.
you need to turn your homework in at this date. This day is when the test is. Um, and then when you get to college, it's even worse because there's like pretty much absolute freedom except for the deadline. So the deadline is
Right.
what keeps you in check.
Yep.
So
Yeah.
like the deadline is that guy behind you whipping you, making sure that you get the stuff done that you need to get done, and then you're just kind of trained on that stimulus your whole life, and it's like it's not necessarily like I should get this done. It's like I need to get this done, if that makes
Hmm.
sense. Yeah, it's it's really interesting, and I wonder how that might change through time as schooling changes, and um, that had to have always been the case, though.
Yeah, I think
Just
so.
like
I mean, yeah, yeah. Much as technology has changed so many things about schoolwork, but you know, I guess that I keep getting ads on my YouTube feed for this like AI scheduling tool. And I kind of want to try it. Not that I would actually, I mean, I do everything in Google Calendar. I'm very manual. You know, I would do it with sticky notes on a big board if I could carry that around with me everywhere. But I've been tempted to give it a go and just see what it would do with my schedule. Yeah, maybe it would be really good, and I'd suddenly become this super efficient being who had, you know, actual time to do things other than work occasionally. I mean, I do occasionally, but
Yeah.
every time I go on vacation, I come back and I'm always like, right, I'm going to change how I do things. I really enjoyed vacation. I want to do this more often, and then I forget, and another year goes by. But anyway,
Well, then you're stacked with like 5 more deadlines, and
yeah,
there's
that's right.
not.
Because as soon as I come back from
Yeah.
vacation, it's like, oh, here are all these things that are piled up, and like, yeah, you
Hmm.
know, it also depends, like, you know, how good other people are about relying on you to do things at the last minute or, you know, short notice. Like, I have so many things that are due, um, well, things that either I have due or other people have due, and they need stuff from me by the end of today. And so, you know, I was up till like after 1 o'clock doing writing up some data I collected for some students who were putting, not my students, but in engineering, and they have this big conference deadline coming up, and it's an engineering conference. It's different. So for, you know, for us, when we write an abstract, it's rarely more than 300 words, and if it doesn't have a whole lot of detailed results in it, that's okay, you know. So I get my students to write their abstracts in advance, but I typically bash mine out in about 10 minutes, you know, an hour or so before the deadline. I probably shouldn't be saying this out loud on a podcast, but anyway, I mean, you know, usually it's been stewing in my head for a while, so it comes out, you know,
Yeah.
fairly fully formed. But yeah, these ones in engineering, they're like 20, 30-page papers. And so it's really like a whole journal manuscript, and I didn't fully appreciate that. So anyway, I mean, this is another thing we can talk about, though, is like, you know, as I've moved from more traditional geology into the stuff that I do now and started working more with you know, people in the engineering college, and also trying to get you know, funding through you know, small business, the SBIR grants that NASA does, which are with you know, companies. The working with engineers has been fascinating to me, and like the differences in culture and the importance of being able to communicate effectively, um, you know, with a team with diverse backgrounds in terms of just, you know, what subject they got their degrees in and what classes they've taken, and that. But even if you have, in theory, you have the same knowledge in common, you might talk about it very differently, use different words, and maybe think about it differently as well. So, anyway, that's a thing that I've have both enjoyed and at times been massively frustrated by over the last 5 years. That's anyway.
Yeah. It's funny you mentioned that because the last episode I had was a couple days ago, and we talked about this exact thing. It was with the director of the TACC, so the Texas Academic or Advanced Computing Center.
Hmm.
And so he's like on this kind of fringe, like he's teetering the line between engineering and science because he's got to talk to all these scientists and make sure that his computers work for their projects. But then he also has to worry about like the practical engineering side of like,
Yeah.
okay, how many GPUs do we have? How much money? Like, what is our budget? How do we? What should our GPU to, I don't know, CPU ratio be? And like this kind of thing. And really interesting topic. And we like I would love to talk about it, and I'd love to ask you where you think like um in a project, so there's like this science side of it, which is like trying to push the unknown, and it's trying to find novel ideas, and so your imagination is kind of the limit. And then there's also a balance between engineering and like, okay, we actually need to be practical about getting these ideas done. And then a lot of the times you take already existing ideas and you try to either, you know, shave them down to be more efficient, like a reduction of known methods, or it's little tweaks here and there, like don't fix it if it's not broke. I'm wondering where you find almost like a philosophic balance between those two.
Yeah, so with the you know with most of the just small scale collaborations I've been involved in, basically I have a lab that normally you'd be more likely to find in engineering than in or material science is really what it is, but it's not something you normally find in geology. But I have equipment that engineers are really interested in the data, and I suppose to some extent they'd probably be happy just to come in, use the instruments, and then just leave. Um, but first of all, they're very expensive instruments, so I'm very protective over them and generally insist on running them myself. And that's based on long experience of them being damaged at various times. Um, but but also, the interpretation of the data, it's not, these are not, I do regard each measurement as kind of we generally call them experiments because we're not sure what we're going to get. And then when you get the data, like the example I'm kind of thinking of as I talk about this is calorimetry. So calorimetry is the measurement of the heat content of materials. So basically, you heat up a sample and you see how much energy it requires to heat it up. And normally, that is just the heat capacity. So, for water, it's 4.2 joules per gram per Kelvin or per degree C of heating. For rock, it's much lower, which is always fascinating to me that rock, it's generally around 1 gram per joule per gram per Kelvin. But anytime there's a phase transformation, so let's say if you're going to melt a rock, then suddenly there's this huge amount of extra energy you have to put in order to melt the rock. So this is the latent heat or hidden heat, as opposed to the regular heat capacity, which is called the sensible heat, which my favorite term in all of thermodynamics. But it just means it's the heat that you can sense and feel. So anyway, so we often get these heat capacity curves that not much is happening for a while, and then suddenly there's a big hump in it. Well, I know that that's a phase transformation. Something is melting or something's happening. But then trying to convey that to a student coming in from they have their thing, they know what their material is, but they may not have done calorimetry before, and they would prefer to just take the data. The computer gave them the data. Here are the numbers. Put this in the model. But no, you got to think about it because maybe in the calorimeter we're heating up at a specific rate. Maybe things are different in your model. Maybe the process you're trying to model is heating at a faster or slower rate, or anyway, there's all kinds of things translating what happened in the instrument to the application in the real world, and I always want to talk through this with them, and and anyway, I mean, usually they're kind of into it, but it's the importance of not just taking the numbers out of the machine. Oh, significant figures. That's another pet peeve I have is because the computer will spit out these measurements with 6 significant figures, and yeah, I know it's not that precise. It's just those last 3 figures are just delete them. They're not they don't mean anything. But anyway, that's actually another really big thing. And this goes back to something actually I was told as an undergrad. So I was undergrad back in the UK, and in a lot of people. A lot of people were going to go on to careers that were not in the subject they got their degree in. And we were told that the City of London, so essentially the British version of Wall Street, likes to recruit geology students because we're very comfortable with incomplete data sets. And that's another thing that I've noticed is that, I mean, it's true, maybe sometimes we're too comfortable with it, I don't know. But as geologists, especially if we're working in the field, we only get one view of something that usually happened a long time ago, based on whatever the exposure at the surface is today. Sometimes you can get geophysical data and see the third dimension, but we know that the process happened in 4 dimensions. It definitely, happened in time, usually a long time in the past, and we have to kind of factor all that in. Yeah, whereas some other disciplines are very, focused on very precise measurements, but then they freak out if they have large uncertainties in their measurements, or if there are just gaps in the data. So I don't know. I like the way that the geologists are trained. I think it's useful for approaching, understanding the world, because we all have very incomplete data sets about the world. So it's,
Yeah, there's an art form to moving through uncertainty in science and also in life, but that's a separate conversation. Um, Especially when you talk about like planetary science, we have like we know a lot about the Earth, but actually sampled and like how much of the Earth have we imaged and sampled and how much do we actually know? Like the whole field of geostats will tell you that we basically know next to nothing about certain areas of the Earth or certain areas of the subsurface. And so then we start to think about other planets, and there's entire fields of science that revolve around, phenomena on other planets that you yourself have delved into. You really start to find so much uncertainty, and you really have to use that intuition that you were trained for in geology to find ranges of uncertainty, try to slowly narrow down the problem that you're looking for.
yeah, absolutely. I think right. I think planetary science does this more than regular geology. Of course, a lot of planetary science is physics and chemistry and atmospheric science and astronomy and things as well. But yeah, so and of course, yeah, when they're sending a rover to go do something on Mars, then I mean that a group of people that really pay attention to their uncertainties and want to be totally honest about them, and um, because as we know, we like to go around testing hypotheses, but you can only falsify a hypothesis. You can never prove it. You can find lots of observations that are consistent with the hypothesis. It still doesn't mean it's correct. It just means you haven't managed to falsify it yet. So, and when you're doing that on another planet, when you only have like one shot, and I mean, first of all, you're hoping that you're going to find a relevant rock that the rover can go look at. But then when you get there and it looks at it, what measurement are you going to make, and can you say that two things are definitively different, or is there a, if they overlap at the 95% confidence interval, then that means one time in 20 or so, they, yeah, so that it means that that they, you can't definitively say that they're not the same, even if the points plot here and here, but once you put the error bars, they overlap. So it's really important to know how big those error bars are, and yeah, I'm always impressed with the amount of testing and rigor that goes into checking all that. Like Mars sample return, I forget what fraction of the tubes they're bringing back are the witness tubes that they've done literally nothing with. But it's so that they can see what does a tube look like that we didn't do anything. We didn't put a sample in there. It just rode around on the rover. But that gives you a baseline, because maybe we'll see this thing in all the other samples and get really excited. But if we see the same thing in the tube where we didn't put a sample in there, then it's I don't know what would have caused that, but some kind of chemical reaction on Mars or something. Anyway, so yeah, I have a huge amount of respect for the people that that do this and are very very careful. Anyway, and one reason I like teaching planetary science actually is this is part of it. The planetary science class I teach, because I'm still relatively new to planetary science, I would say. I mean, I was never formally trained in it. probably shows sometimes. Everything I've learned is from going to conferences, listening to people speak, talking to them, reading papers, and so on. And but the class I teach is mostly focused on how we know what we know, or think we know what we know. It's less a it's not a complete tour of the solar system. It's not a detailed dive into all aspects of planetary science because I lack the background for some of that. So we focus on planetary geology, but it's always, how do we know this? So, final exam question, if anyone, and I tell everybody in the class this anyway, not that not that they seem to pay attention, but I always have a final exam question, which is, you're on a spaceship, you arrive at a new planet. This is actually it's a scenario that's from one of the Foundation novels by Asimov. They arrive at a new planet, and the first thing they do is they make a bunch of measurements to figure out some basic things about the planet. And so so I ask, what observations do you need to figure out, the approximate density of a planet, and then once you've got the bulk density, what can you say about its composition in very broad strokes? Anyway, yeah. So I always loved history and philosophy of science. Actually, as an undergrad, I took a course in that. I was better at that than I was in geology, but there are more career options in geology, so that's the route I went. Yeah, I love kind of opening students' minds to these things as well, because I think a lot of education, perhaps especially in geoscience in Texas, tends to be very industry oriented and very here are the things that you need to memorize, I mean, hopefully there's lots of thinking going on as well, but I feel that the more philosophical aspects of how do we know things kind of gets glossed over. So
yeah, you're kind of given systems, and I guess I can say this because I don't have anything. I won't receive any backlash for anything I say right now. I'm too unimportant. But you're basically given all these systems and things to memorize, so you can go in the oil industry and find hydrocarbons for the rich people that want you to. It never ceases to amaze me how planetary scientists do what they do. Like the fifth order things that they're figuring out, or this system impacts this system, which impacts that system, which impacts this system, and we can measure that system and basically integrate for what the original change was, or try to figure out what's a good example, stuff to do with Jupiter, and trying to figure out and you use a lot of first principles. It's a lot of fundamental physics and fundamental chemistry, and maybe a better example is the moon system. I was talking to, I don't know if you've ever met a guy named Doug Hemingway.
I know the name.
He's a planetary geophysicist at the Institute for Geophysics here in Austin.
Okay.
And I remember asking him, just out of curiosity, one day, I was like, how did the moon form? I know there's different theories, it's a bit debated. And he's like, well, it's still kind of up in the air, but there's been new research that's come out that there was this whole problem where when we went to the moon, we got samples, and the chemistry of the samples wasn't in line with what our model said the chemistry should be.
Yep. And
so, correct me if I'm wrong, I'm pretty sure that the moon had really similar chemistry to the Earth in the actual samples that we got. But the samples that were predicted, the samples that would have been predicted by the model, showed that the moon's chemistry should have been pretty different from the Earth. It should have been more like the satellite, or the smaller planet that crashed in the Earth, if the impact theory is
right.
the theory that you subscribe to. And they came up with this whole thing about like evection resonance and how like they're like really using like fundamental physics and like Kepler's laws to try to figure out what the physics of that impact would be, and then they were able to model it, and then their model matched the chemistry, and it's I don't know, it's just really amazing how they came up with that. And is that whole like process of figuring out a problem that's shrouded in uncertainty or just like absolutely caked in uncertainty what kind of drove you towards planetary science, or was it something else?
So yeah, that's a good question. I'm trying to remember how I did get into it now. Um, it's probably partly through teaching. Again, my wife's an astronomer, so when we were at the University of Missouri, we decided to co-teach a course, and in those days, that we called solar system science. It was half astronomy, half geology. So I basically did terrestrial planets, and she did the sun and the gas giants, and she did most of the physics, and I did the chemistry and mineralogy. Um, and I think it's once I got into volcanoes and then realized that there are volcanoes outside of the Earth as well. And yeah, I just got really interested in that. I don't know. I find the idea of all the different possible compositions and sizes, and of course, gravity is different on different bodies. So Jupiter's moon Io is the most volcanically active body in the solar system, but Io is tiny and has a really low gravity. It's approximately ballpark similar to our moon. And so when it erupts, it flings stuff out and it travels so far. And and now of course exoplanets, which when we started, I guess when we started teaching that class, the first exoplanet had been found at that point, but I didn't know anything about exoplanets till just a few years ago. That's actually been this whole new frontier now for experimental petrology. So, which I guess is what I do, kind of. I describe it as experimental volcanology mainly because my application is generally understanding volcanic processes. But the bigger distinction there is that I tend to work at atmospheric pressure. And most experimental petrologists work at high pressure. And indeed, the march of experimental petrology from the 60s through to the present day has been a constant quest to go to higher and higher pressures, in combination with high temperatures as well, to try to do experiments to see what minerals form and what their properties are at the actual conditions of Earth's core, or the interior of other planets. And I kind of felt that was approaching an end point. There's still lots of vigorous debates about what is in the Earth's core. Everyone agrees there's some light element in there, but exactly which light element it is, people argue about still. I think that's been going on for at least 25 years. But yeah, suddenly there are all these exoplanets, and not just a couple, but we have thousands now cataloged, with the assumption that as our techniques for spotting exoplanets improve, because right now we can detect them through 2 or 3 different methods, but in general those methods are quite restricted to large exoplanets that are close to their star. And as but already they've discovered thousands, and as things, as telescopes improve, and we're gonna end up with tens and tens of thousands of these things. And now, amazingly, people are starting to look at the atmospheric composition of exoplanets. Um, we're going to start finding just very simple, observations. But if you know what the atmosphere is, that already places a lot of constraints on things. Of course, people are looking for biomarkers, biosignatures, and so on. Um, But suddenly we instead of just focusing on the interior composition and conditions of the Earth, we've got thousands and thousands of other bodies where generally we don't know what their bulk composition is. But yeah, suddenly a whole different range of pressure temperature conditions, possible compositions. So there's, the experimental petrology just has so much work in front of it. And of course, this also happens to coincide with the real development in AI. So it wouldn't surprise me at all if well, I know experimental petrology is already making use of machine learning and AI, but I wonder how much that is going to replace actual experiments. Um, I'd be sad if it totally replaced experiments because AI can only do what it does based on its training data set, and a bigger and better training data set generally means better predictions. But anyway, I'm rambling now. But
No, this is all great stuff. Yeah, I talked to the director of TSCC last week, and
mm,
he was talking about how, um, or he was on the subject of like AI, what that means for the future, what could that mean for replacing people or helping people out or whatever in the field of academia. And he was like, okay, what if you had, because AI is not infallible, right? It'll get the wrong answer a lot of the time, but neither are people. And people, I think, to a lot more of a degree, will get the answer wrong than AI. And so imagine you had a grad student, and it seems like, I'm not sure about working in a lab or doing experiments, but for like the research that I've been a part of, which is more on like the geophysical computational side, it's like, okay, read all these papers, see what problem interests you, try to come up with a hypothesis, and then see like how you can test that. And I'm going to help you along the way, and you could kind of come up with this idea on your own. Imagine you had AI and you said, okay, instead of reading 25 papers, read 250,000 papers, and it'll do it in a couple minutes, right? And then from that, tell me what you learned, and then try to come up with a hypothesis, and then come up with an experiment that can test that hypothesis, or come up with multiple experiments. And you could eventually run into like AI taking the literature and then coming up with an experiment on its own, and then through like robotics and automated experiments being able to run the entire experiment itself and then give you its results at the end, which is a really weird future if that does come true for a lot of different labs.
yeah, all right. So that leads me to two thoughts. So the first one, humans are still better than AI at knowing how many fingers should be on a hand. But anyway, that's um, so no. The first real thought is if an AI trolls the literature and comes up with a bunch of stuff. First of all, you have to be careful about which literature it's looking in and whether the AI has a way of processing the fact that a paper from the 1960s is likely to have very good data in it. The interpretation of those data we may now disagree with. So, for example, in the late 60s, the plate tectonic revolution, that completely changed science. It doesn't mean that all of the geologic mapping and research that was done prior to the late 60s is wrong. Of course, the data are generally correct, no less correct than anyone mapping today usually. But the interpretation might be completely different. So one question is whether the AI can satisfactorily distinguish between, results and the results and discussion parts of a paper, right? So the results describe the data, and including any shortcomings in the data, what the uncertainties are, any experiments that seem to have not worked or produced just utterly bizarre results, that kind of thing. And then the discussion is usually where you put it in the context of the current paradigm. So I could imagine. I mean, not that it would be bad to have AI thinking about older paradigms as well, because sometimes there are parts of geology where old ideas come back, and they so we kind of oscillate over time between how we think things work. Um, but the other thing is, I'm not sure that AI is then going to engage in any paradigm shifting research, because if it's trained on everything that on our current and maybe previous paradigms, I think that's what it's going to feel boxed in by. I don't see it coming up with something, a whole new paradigm. I mean, not that these things happen very often anyway, and they're also often quite unpopular when they do first happen. Vagueness, continental drift. His presentation to the American Association of Petroleum Geologists being a famous example of, a really impressive data set. What his weakness was in the discussion part. He had the observations, he just couldn't really explain them, and people weren't willing to buy that. Or at least a lot of people weren't. And it was better received in Europe, I think. But anyway. So yeah, I mean, for sure, AI is going to have a lot of uses. I of course worry about the malign uses of AI, but hopefully that's not such a big deal within geology. Yeah, but I'm not sure that AI is going to have the creativity. I mean, I really think that is. I mean, lots of people have said this, in many contexts, but I think that's the biggest issue is it's trained on things. It's very good at better, certainly a lot faster than people at doing things based on its training data. I don't think it's very good at extrapolating or creating new ideas. But I may be wrong, and maybe there's technology around the corner that will change that. Then there was another thought, and of course it's escaped me now. What was it? So we got, right, it can't extrapolate, and nope, I've forgotten what the other thought was. It'll come back to me.
Yeah, feel free to interrupt me if it does. But yeah, I think a good phrase to sum that up is competence versus comprehension. It's like AI isn't really comprehending what it's doing. It's just predicting, like if you have a large language model, it's just predicting what the next word should be based on the data that you give it. Or if you have an image, it's like predicting, in this huge, so turns all that data into like this huge vectorized space and then does a couple transformations. And at the end, it'll, have like this, 4,000 dimension vector that has like different probabilities based on, all the different objects you would give it. And then it'll say like, okay, 96% chance that this picture is a hot dog. But it's not really comprehending that it's a hot dog in front of it. It's if it does understand the world, it understands the world a lot differently than we do. And then the same exact thing just happened to me. I had an idea, and then I started talking about something a little bit different, and then the idea completely evaded me. Oh man. A question that I did have when you were talking about exoplanets was atmospheric constraints on volcanism itself. So I guess if you were looking at the Earth from, a telescope on another planet, would you, from the atmospheric composition, be able to discern like how much volcanism there is and what type of volcanism we have?
So it's a good question, and we're approaching the limits of my competence here. So I will, I'll throw that caveat there. I think the first thing you would notice, because I think in general we're not able to do spatially resolved spectroscopy of atmospheres around other planets, outside the solar system, exoplanets. So, if Earth filled 1 pixel and you just had, some kind of bulk atmospheric analysis, um, I mean, the first thing that would jump out at you is oxygen, right? So that would be something that would need to be explained. I mean, there was cool news, late last week, I think, with the discovery of this abiotic oxygen generation on the seafloor. That was pretty cool. So these rocks are just spontaneously themselves reducing and then releasing oxygen as little gas bubbles, but there's no bacteria involved. But anyway, most planets that we're familiar with don't really have free oxygen, and the only reason we do, in the amount that we have it, is cyanobacteria and photosynthesis and so on. So yeah, so there's that. Now that's totally separate to volcanism, of course. So I'm just prevaricating because I don't really know the answer. But I mean, sulfur is a thing that I would certainly look for volcanic activity. Because the main volcanic gases are, first of all, water. Okay, but water in the atmosphere could just come from evaporation of the oceans. CO2, well, lots of things can have CO2 in the atmosphere, and that doesn't have to come from volcanism. Sulfur, well, again, does sulfur have to come from volcanism? I mean, look at Venus. Like, we think Venus is actually volcanically active, but I don't think volcanoes put all of the sulfur into Venus's atmosphere. But maybe I'm wrong. We're absolutely at the limit of things that I know here, so I should shut up. But yeah, but I think sulfur is probably the thing that I would look for. Yeah, whether that's necessarily diagnostic of volcanic activity, I don't know. Yeah, and of course you can't really look for temperature because Earth's average temperature is the atmospheric temperature is not affected by volcanoes. So, but yeah, I mean, I think mostly I'd go if we have some idea of how old the planet might be, and I'm actually not sure how we would know that. That's a thing I need to look into. Um, and its size, then to some extent you can probably guess whether it's like to be volcanically active just on the basis of whether it's cooled down to the point where it can't be anymore. So, the Earth is, we think that Venus is, there's certainly recent volcanism on Venus, geologically speaking, so a few tens of millions of years. Likewise for Mars. So bodies of that size, and of course Mars is quite a bit smaller than Earth and Venus, can stay volcanically active for several billion years. Whereas the Moon, well, the more data we get back from various Chinese rovers and sample return missions, the more we're finding out that the Moon seems to have had a volcanism that went on for longer than we had perhaps realized. But still, there's no suggestion that the Moon is volcanically active today. And Io is, but that's only because Io is close to Jupiter and it gets this tidal heating. So as it orbits Jupiter, it gets squeezed and stretched and squeezed and stretched, and that keeps the interior hot. Anyway.
Yeah, earlier you mentioned that you enjoyed thinking about all the different possible lavas and the different combinations of what things could be, and the different pressures and temperatures that create different materials. And I do want to kind of ask about your general motivations for volcanism and studying lava and petrology and igneous petrology. And is that like a big motivator of yours, just like all the different novel combinations of stuff that goes into creating new lavas and things like that? Or
Yeah, I mean, so right, I would like to I'd like to be able to say that it was some noble drive to save lives or something like that, and it's totally not. Not that I'm against saving lives. I am in general in favor of that. But I don't know. I'm not sure exactly how to explain it. I definitely have an affinity with molten lava. I like, I playing with it in the lab. I mean, I'm not sure that, of course, we play with it carefully because it's very hot, but doing experiments on it, seeing when it crystallizes, when it quenches to glass. I don't know. I feel like I have a personal relationship with the lava, and it's probably a strange thing to say, but that's what it feels like somehow. Um, and it's also interesting to me how many applications there are for for this kind of understanding. So, yes, the next time Mauna Loa or Kilauea erupt on Hawaii, it would be nice to be able to. We try not to use the word predict, but to, let's say, forecast different hazard scenarios. So one motivating thing there really is to be able to provide useful data to the civil defense and the U.S. Geological Survey as they're trying to map out what areas might be inundated with lava over what time frame. Generally, those lava flows don't kill people, right? Occasionally they do. So the famous example is Nyiragongo in the Democratic Republic of Congo. And Nyiragongo produces very fluid lava, which we've actually studied in the lab. It's it's hot, it's fluid, as is most lava, I guess. The really dangerous thing about Nyiragongo is that it can erupt from fissures that are basically on the edge of the city of Goma. And Goma didn't used to be as big as it is now, but it's right on the border with Rwanda, and it grew
Yeah.
hugely in population during the civil war in Rwanda. So there've been eruptions there in 1977, 2002, and just a couple of years ago, I think it was 2021. And I think it was 2002. There's a famous video of lava flows coming through town, and it actually inundates a gas station, which then explodes. And I believe that
Oh man.
explosion killed quite a few people, and some
Yeah.
people were just basically cut off and killed by the lava. But that's a really unusual situation, and really on almost no other volcano in the world is that really an issue. I mean, we've seen the eruptions in Iceland where you know they managed that really well, and people were able to go up very close to the active lava flow, and everyone was just sensible, which is almost surprising. But anyway, so the real dangers from volcanoes are much more to do with explosive eruptions that produce fine-grained volcanic ash. You could get the dense clouds of ash that can flow long distances at very high speeds, faster even than Pierce Brosnan can drive, in fact, despite the beginning of Dante's Peak. Um, but the problem with those is like there's no escaping a pyroclastic density current. So if it happens and you're in the zone, it's going to inundate. Then you don't have time to escape. So anyway, back to lava. So in terms of being able to assist with forecasting and at least probabilistic hazard analysis, most likely where is the next lava flow going to go? How long would it take to get there? That's useful. But it intersects with so many different things. So we've done a lot of experiments with obsidian, right? And we end up talking to archaeologists, and we get into discussions of the chemistry of obsidian, which people use to track which precise quarry did this piece of obsidian come from. And now you find it, not only in another state, but maybe in another country, at some archaeological site, and they establish trade routes and so on. That's really fascinating. What makes good obsidian from bad obsidian for making arrowheads, for example, or other implements. So yeah, there's that. More recently, we've been working on in situ resource utilization on the moon. So with the idea is that the Artemis program will result in a probably permanent base camp on the moon's surface at some point. Um, I think anyone who tries to put an actual year on when that would happen is anyway.
It's like it's one of those fusion power, always 6 years, always 8 years away.
Yeah, right. That's
Yeah.
anyway. At some point, if there's a geopolitical will, then it will happen. And it's very expensive to carry things into space. It's cheaper now than it used to be. Reusable boosters and things like that. But so what people are looking at is how do you use the resources that the moon has, and of course the main resources that the moon has is dirt. But of course we call it regolith because it sounds more like science. But yeah, it's the fine-grained rock that is on the surface of the moon. And why is it fine-grained, right? It's not because it's not wind-blown sand like a desert because there's no atmosphere and no wind on the moon. It's not mud deposited by rivers because there's no rivers on the moon. It's really interesting to me, actually. So I have a student who just finished up an internship. Today's his last day at Johnson Space Center, and he's in their simulant development lab. Um, and so we've been working on, with lunar simulants for a few years now. We're trying, or people in general are trying to develop the most accurate thing to simulate the actual regolith on the moon. We do have a few samples from the Apollo mission, but of course they're very valuable and nobody wants to get those out just so engineers can drive a rover over it to see how it behaves or something. So we're trying to develop the best simulant for the regolith that's possible. My interest is mostly in heating it up and melting it, but that will have several applications, right? So you can potentially make bricks, because the regolith itself is fine-grained powder. It behaves differently to fine-grained powders on Earth because it's got all these really weird irregular shapes. So it kind of sticks together very well. It's actually, the Apollo astronauts found they could hammer in a drive tube, which is just like a tube of metal essentially, to try to extract a core. They could drive it in maybe 50 centimeters, foot and a half or something, fairly easily, and then it became almost impossible to go much further. When they dug a trench, they shovel it, scoop it away. The side of the trench is pretty much vertical, and stuff isn't falling down. That doesn't happen if you try to dig a hole in sand or something on the Earth. The sand will fall in the hole until you're at an angle of repose at, 36 or 40 degrees or something. But yeah, these really weird shapes, and these are fascinating. These are called agglutinates. They're caused by micrometeorite impacts. And that's one reason that we need good, strong shelter for a habitat on the moon. There's radiation, but there's also just these micrometeorite impacts. There's no atmosphere, so any bit of dust in space that hits the moon, it doesn't slow down before it hits the surface. So it can be traveling at several kilometers a second. Tiny, tiny things, and so they make a tiny, tiny little crater. And locally, the energy of the impact mostly goes into heat, and it melts the grains around them. And we're talking like on the scale of something that's less than a millimeter here. So these agglutinates are often just a few tens to a few hundreds of microns in size. Really weird shapes, so they interlock. And so it just has different properties to the Earth. Anyway, my main interest is in melting it and making either bricks or there are other uses for glass as well in the future. And then of course there's a lot of other people looking at extracting oxygen and metals because when you get down to it, it's not when you melt the stuff, it's a lava that is not too different in composition from terrestrial lavas. There are a few differences, like depending on where you are on the moon, the melting point might be really high. We're targeting South Pole as a place to go because there's the possibility of having pretty much permanent lighting if you go to the right spot on the South Pole. Also, that's probably where the water is. However much is there, we don't know. Hopefully NASA will not cancel the Viper rover and it will go and we will find out how much water is actually there. But anyway, we'll see what happens with that. But yeah, the rock at the South Pole, the anorthosite, we have anorthosite on the Earth in various places, but it has a really high melting point. So anyway, so it's interesting playing around with these things and seeing what can we do with it. Yeah, got off on a bit of a... I get excited about regolith and simulants, but anyway.
No, I love it. It's all really cool stuff. There are so many questions I could ask. I was like, I kept writing down things as you were talking. I guess I'll start with what is the elemental composition of the regolith that you were mentioning?
So the mineralogy of the moon is mostly pretty simple. When you get into the trace minerals, there are some fancy things, some of which are only found on the moon. But most of the moon, certainly from a petrologist perspective like me, oh, I should stop and define petrology actually just for a second. So petrology is the study of rocks, which is not that fashionable in geoscience anymore. There's a lot of scientists and geoscientists that don't look at rocks very much. I mean, so the positive thing there is that we've included, the atmosphere, the hydrosphere, the biosphere. These are all really important parts of the Earth system, and it doesn't make sense to look at rocks in isolation. The downside is that sometimes people don't get as much mineralogy and petrology training as would be helpful to them in studying the interfaces between the solid Earth, the oceans, the atmosphere, and so on. Anyway, so petrology is the study of rocks, mineralogy is the study of minerals, and rocks are made up of usually many, many crystals of one or more minerals. So on Earth, we might be familiar with sandstone, which is made usually mostly of quartz, just lots and lots of quartz grains. Certainly around here, and most of the places I've lived in the US, we're familiar with limestone, which is made almost entirely of calcite. But again, one rock will have many, many crystals of calcite in it. So the rocks at the south pole of the moon are called anorthosite. And these are made almost entirely of plagioclase feldspar, which is a calcium-rich aluminosilicate. If you've ever seen the kind of dark-colored countertop, it's kind of a dark green with quite big crystals, and as you walk past it, they'll just catch the light and really shine brightly at you. That is what a really good quality anorthosite can look like. They're absolutely beautiful. Anyway, so they are found and quarried on Earth for countertop purposes mostly. I've got a nice bookend somewhere made of the same stuff. And on the moon, the anorthosite is mostly made of this high calcium feldspar. It's actually higher in calcium than the feldspars on Earth usually. Elsewhere on the moon, you'll also find olivine, which is also common on the Earth, ilmenite, which is an iron titanium oxide, and pyroxene, also common in igneous rocks on the Earth. But that's basically it for most of the mineralogy on the moon. It's pretty straightforward. So this feldspar has a really high melting point. If it were pure CaAl2Si2O8, which would be the anorthite end member of plagioclase, its melting point is 1553 degrees C, which is 3,300 Fahrenheit plus or minus, something like that. So it's really hot. We can melt that in our lab. Many people have equipment that you can melt that with, but it's very expensive in terms of energy to do that. That's one thing I am grateful for, is I don't have to pay the electricity bill for my lab. But anyway, again, shouldn't say that out loud. The university admin will get ideas. So. Yeah. So if we're going to melt these things and then pour them to make bricks or something, then that needs a lot of energy, and that's one thing that we don't have a lot of on the moon. Um, you know, there have been a few calculations. I did this a few years ago, and I forget what the answer is, but the amount of photovoltaic cells you would need to put on the moon to generate enough energy to be routinely melting these rocks. Um, and again, then you've got to get the photovoltaic cells up there in the first place, or you can use the regolith to try to make them. And so that's various people at different companies are looking at all these kinds of things. I think that'd be really cool once you get a self-sustaining photovoltaic cell manufacturing process underway on the moon. Then you can really plan for growth and sustained settlement. Again, you got to ask why would we want to do that? There are advantages to being in the low gravity of the moon compared to the Earth. If you want to go to Mars, it makes sense to stop somewhere along the way and fly to the moon, fuel up there, and then go to Mars. Is a lot better than trying to go directly from the Earth and climbing out of Earth's gravity well. But you could also do that with a big space station in cislunar space, maybe somewhere between the Earth and the Moon, so the NASA Gateway program is the plan for a space station. Anyway, I got off the topic of regolith. Let's go back to that for a second. So one thing we've been doing, I talked about the agglutinates earlier, which are kind of already half melted and kind of glassy, and so glass becomes liquid when you heat it above the glass transition, which is usually around 700 degrees C, or like whatever that is, 1500, 1400 Fahrenheit, something like that. So one thing we've been doing is playing around and showing that you can actually potentially make a brick. If you collect all these agglutinates and glassy material on the moon, you can probably make a brick at a much lower temperature, with a lot less energy cost than having to completely melt crystalline feldspar. Anyway, that's kind of one application of what we're doing. I think I lost the thread of the question I was trying to answer there, but this happens.
No, it's okay. No, you answered it perfectly. I mean, I was just asking you about the mineral composition and elemental composition of the regoliths you were talking about.
Yep.
So elementally, what are we seeing in the regoliths that you're talking about? Is it a lot of silica?
Always lots of silica. So near the South Pole and in the highlands. So again, if you look at the moon, you'll see brighter, more reflective areas and darker, less reflective areas. So the bright areas are the highlands, which are made of the anorthosite, and the dark areas are what are called the mare, which is Latin for seas, because originally people thought maybe they were oceans. And those are they're younger than the highlands. These are actually areas covered in basalt. So in the highlands, where it's mostly feldspar, calcium, aluminum, silicon, oxygen, of course, are the main things that are there. In the mare, you get a lot more iron, magnesium, titanium, but you also have calcium, aluminum, silicon. But those are kind of the main elements. So in a way, what's kind of missing is a lot of the things that we get at the surface of the Earth due to the surface processes we have involving the atmosphere and water. So you go to Enchanted Rock, for example, to use a local example, but an outcrop of granite, and there's a creek that you have to cross over to get to Enchanted Rock, and the sand there is just full of bits of the granite that have disintegrated into individual crystals. So there's a lot of feldspar, some quartz, some mica, and then that sediment gets washed down the rivers and ends up in the Gulf of Mexico. But along the way, it starts to the potassium feldspar will start to break down and turn into clay minerals. The potassium will end up being dissolved in the water. Anyway, so but essentially you get a lot of clay is where I'm going with this, or mud, and we're quite familiar with this on the Earth, but you just don't get that on the moon because it's very dry. I mean, there is a little bit of water, we think, on the moon. That there is some water in the Earth's interior, but we're talking about trace levels where people with the right equipment can measure it, but you know, it's not like you could grab a rock and squeeze enough water out of it to have a drink. We're talking the part per million level by weight, maybe
Yeah.
a few ppm. So yeah, but in terms of the industrial, not that we're ever going to have a huge industry base on the moon, I don't think, but in terms of making photovoltaic cells or making other things, metals for fabrication, iron, titanium, that kind of thing. So that there are several useful things. So yeah, the Mare have more iron and titanium. That's where you'd want to go to if you wanted to make really metal feedstock on the moon. Also, that's how you can extract oxygen. I think the main process is reduction of ilmenite to liberate oxygen. I think it's harder and takes more energy with the calcium feldspar in the highlands. So. Which then leads to the question: we're gonna, is there going to be a railroad or something like that built on the moon so we can shuffle stuff, back and forth between the Mare and the highlands? But then another thing I like thinking about here is, whenever you have an impact on the moon, you spray stuff, usually downrange. So the impactor comes in, and then the stuff mostly sprays out in that direction because of momentum. But when that happens, you're excavating material, and then you're spreading it around elsewhere. And of course, this has been studied on the moon a lot because one of the way we tell the age of the surface of different places on the moon is by the density of craters. But of course, if you get the right crater, it could land in the highlands, and then it could splurge highlands material onto the Mare. Or you could have a crater on the edge of a Mare, could splurge Mare material onto the highlands. So there's quite a lot of mixing going on. And if you chose a location carefully, you could probably, be in the highlands, but have easy access to Mare material that had been put there by an impact. Anyway, I'm sure that the companies that are looking at actual, resource exploitation and essentially mining on the moon have looked at that and thought about it much more than I have. But
Mm-hmm. Yeah. So I was gonna ask you about how there's not a lot of erosion on the moon and how that affects the moon, but it seems like there is some to an extent with the impacts that you're talking about and material being moved. But compared to Earth, is it anywhere close to the amount of erosion we have here?
no. So now, but of course, what I really want to go do is go there and do some field work, and then I'd have a much better perspective on it. But it's not going to happen. But I have spent quite a bit of time going to talks, and in fact having talks to my class by some of the Apollo geologists, and also Jack Schmitt, the only geologist to have gone to the moon on Apollo 17. And looking at their photos, and there was one I saw recently that I don't know how I had not seen it in this many years I've been doing this, but it was a different view of the side of the Hadley Rill, which was, I forget what I always get the numbers mixed up. Anyway, whichever Apollo mission that was, I should know that. So this was a lava flow that they landed on, and of course, the actual pictures of the surface, it kind of looks like a lot of the rest of the moon, the regolith, right? There's this kind of somewhat fluffy, powdery surface, but you can walk on it fine. You don't sink in very far. Um, but then there are there's kind of a hill there, and that's actually the side of this lava flow. And then so recently it was Jim Head actually from Brown, who was one of the Apollo geologists. He gave a talk in my class, and he showed pictures, and I'd never seen this particular one before, but you could actually see outcrop and layers, which was, of course, we see that from Mars. I mean, the rovers are essentially doing real field work on Mars, which is, just spectacular and wonderful. And, the hope is that we're going to do that with the moon, which you would think, we're much closer to it. Um, but yeah, it's but still, although that particular bit wasn't completely covered in dust, so you could actually see a little bit of layering. Um, but yeah, mostly it's just covered. It's this very fine grained. The surface just being peppered with these micrometeorites and impacts all the time. It just turns it into this dust. Um, So, I mean, there are boulders around as well. It's not like it's all featureless. In fact, that's one thing that the simulants have typically been too fine grained. People have kind of ignored the fact that there are boulders and rocks and stuff in it as well. Um, so it's just very different. And if I could go there, I'm sure give a really good description afterwards. So if anyone wants to fund me, that'd be great. But uh, yeah, but since I'm not going to go there, I just have to rely on the pictures that I've seen from the Apollo mission, and yeah, it's just kind of very muted and I don't quite know how to explain it, but yeah, it's like so things haven't been transported sideways mostly. So gravity still works on the moon. It's just less effective than on Earth. So there things will tumble down the side of craters, and over time, that means that crater morphology, and if everything had a steep side, it'll end up being more gentle sided. Um, but yeah, the rills, which kind of superficially look a little bit like meandering river valleys, well, they were actually meandering lava flows. Um, but they don't really, they only transport the lava. They're not depositing sediment like a river. So yeah, it's anyway. Well, obviously, all I know is from what I've seen in pictures, and but but yeah, it's a very different kind of landscape. That's for sure.
Yeah, and the moon dust is razor sharp, right? Um, I remember seeing it was like some kind of short video somewhere. It was talking about the Apollo missions, and they found that their spacesuits were like slowly getting ripped up by the dust that would stick to it, and it was like so sharp that anytime they moved around, it would just like tear the fabric a
Yeah.
little bit.
So that's yeah, and that's mostly the agglutinates. So yeah, because they are tiny little pieces of glass. That then they're a little different. If you break a glass bottle, you'll get a shard that has really sharp edges, of course. In a volcanic eruption, volcanic ash is actually tiny little shards of volcanic glass. That can be really mean because it's usually formed at the intersection of multiple bubbles. So if you know what caltrops are, the little kind of four-pointed things that ninjas would throw out in front of
Oh
their
yeah.
pursuers. So whatever way they land, there's always a point sticking upwards. So that tends to be the shape of volcanic ash because it's the little junction between several bubbles. And this is why it's so bad to inhale volcanic ash because it is tiny, very pointy shards of glass that then forms concrete in your lungs when you've inhaled it. Um, so anyway, so there's the glass bottle that which is not a particularly good analogy for the moon. There's the volcanic ash, which is maybe a slightly better one. But then the agglutinates, they're just really weird shapes, but they do tend to be quite contorted. But they certainly can be quite sharp and pointy. Um, Yeah, and then and the way the dust stuck to the spacesuit, so that's again, it's more static electricity is more physics than I normally do. But anyway, it certainly was. I think not something they were expecting to be as much of a problem as it was, and also certainly something that's being studied a lot now. But yeah, the lunar regolith is weird stuff. I'm hoping we can get some in this fall. From my student that's working on the simulants, he's really wants to get hold of some the real thing. But of course, all we're going to do is melt it. So in a, which sounds bad, but we're only going to take a few tens of milligrams, and it's in a very noble cause, which is to figure out how much energy would it take to actually, make a glass brick on the moon,
Hmm.
which is something that we don't really know because again we've been playing with simulants, but um, anyway.
Is there a couple questions? I'll start with, so if you have an experiment where you're using like tens of milligrams and you're heating that up and then you're finding, okay, what's the, specific heat capacity or, you know, um, latent heat of fusion of this rock as it goes from solid to liquid or from liquid to glass or whatever phase transition you want to
Hmm.
do with it. Um, does that scale up linearly as you increase the volume, or are there weirder things going on?
Yeah, okay, that's a good question. So the short and easy answer is yes. The the better answer is first of all we do use very small quantities, and so it's really important that whatever we're looking at is representative of the larger thing. So for example, if I was going to measure the heat capacity of a granite, I wouldn't crush the granite into millimeter sized chunks and then just put a couple of them in, because I might just have two pieces of quartz or two pieces of feldspar, and what I need is a mixture that's representative of the quartz, the feldspar, the mica, whatever else is in there. So I would powder the sample really finely and then take a scoop that was still only 20 milligrams, but maybe had, hundreds of grains of powder, and in which case it should be representative. So that's one issue, and that's kind of that's an issue that it's our responsibility to figure out when we're doing these experiments. Then there's the application part, and there it's the responsibility of whoever is using the data. Um, because when we do a measurement, we do it at a fixed heating and cooling rate, usually something like 20 degrees per minute. Um, the faster you heat, the stronger the signal. So that's good. You get a better signal to noise ratio. But also, the faster you heat, actually, there's a thing called thermal inertia, which is, it basically takes a bit of time for the heat to actually get into the sample. And so if you're heating really quickly, the temperature of the furnace is always going to be ahead of the temperature inside the sample. And so if you measure too quickly, we usually find that our sample will melt or complete melting at a higher temperature than we think is the true melting point. And that's just this thermal inertia effect. So we're always careful to point out that all right, this is where we measured this transition, the glass transition, or the onset of melting, the end of melting. But if you were using a process that had heating more slowly, you would see these transitions happen at slightly lower temperatures. It's usually not a really big deal, but when you're talking about what temperature do you need to get to fully melt the sample, then it's quite important, because whether you need to go to 1600 degrees or 1400 degrees, that difference makes a big difference to how you design your furnace and how expensive it would be. Um, but then also, of course, if you have a lava flow, which is a lot of what we use our data for is in modeling lava flows, the whole lava flow doesn't all cool at the same time. Likewise, if you're making a brick, the whole brick doesn't cool at the same time. The surface has to cool before the interior can cool, and you might have different temperature time histories for different parts of the same brick. And the temperature time history is going to determine whether crystallization happens at all or whether it's glassy. And then if it does happen, it'll determine what size the crystals are. And that in turn will determine the strength and physical properties of that brick. So anyway, so there's lots of detail here, which I enjoy thinking about. But yeah, so you have to be careful, because we're making measurements on very small things. I can tell you a lot about that very small sample. There are other things that it's not my job to actually figure out the thermal history of different parts of a brick, but it's definitely my job to help the people that are doing that make sure that they're modeling the brick appropriately. So at least I think that's my job. I don't know.
Who knows? With how interdisciplinary science gets nowadays, it's
yeah.
I had a whole discussion with a guest about the semantics and philosophy of titling your science or titling yourself as a researcher and what you should title yourself as, and the impact of that. Which, if the conversation gets there, that would be a fun thing to talk about, especially with I talked to a igneous geochemist, and he refused to refer to himself as a volcanologist, and
Interesting.
I was a little bit confused as to why. It was like, and then there's people that I'll work with at the Institute for Geophysics who will not call themselves glaciologists, but they do so much glaciology. They call themselves polar geophysicists because they have slightly different methods. We're doing geophysical surveys of the ice rather than, kinematic modeling or looking at sediments under the ice or whatever. But it's so interesting because what you define yourself as and the words that you use will go into your public image, and then as a scientist, and then that goes into okay, I'm trying to write this grant. What do I title myself as? What are people going to know me as if I go give a lecture somewhere, and someone's interested and they look at my academic profile? What is this what is the first impression going to be to kind of see what kind of research that I do? It's such an interesting thing.
That's a great question. So yeah, we can definitely talk about that for a bit. And that, of course, relates to the topic that I think we were going to start with, but never did, which is how I ended up doing what I do now. Because, as I mentioned earlier on, I've never had any formal training in planetary science or volcanology, to be honest. And those are the two things that I've really been doing for the past 15 years at least. It's probably more. Every time I say 15 years and I actually think about it, turns out that it's 25 or 30. So I'm going to stop even thinking about that. Yeah. So how I describe myself depends on who I'm talking to. So I do quite a lot of outreach, hands-on experiments, looking at rheology, because I some of what I do is rheology, which is how material flows and deforms. Mostly I'm looking at lava, but I've got a student in the lab looking at measuring the viscosity of honey as a function of water content and pollen content and all kinds of other things. So anyway, I'm interested in how things flow, usually lava or analogs for lava. But if I'm talking to someone in elementary school, then usually I'll try to say the word geology a couple of times, and I'll probably talk about volcanoes and I'll probably just say geologist. They probably don't know what a geologist is either. Volcanologist is that much harder to say. But anyway, So for outreach, it's definitely I'm gonna focus on something that I think that they might know what I'm talking about. And one frustration I have actually is a lot of the time, even when students, right up through 12th grade, when students do geology, they usually aren't told that they're doing geology. They're often told that they're doing environmental science, which is fine. Geology is absolutely an important part of the environment. The, the, the problem from my perspective is when students go to university, if they know that they liked that, maybe they enjoy physical geography, which I did as a student, and but I've only ever learned about, I don't know, volcanic landforms in geography or in environmental science, then that's what I think I want to do. Except that it turns out that when you get to when you get to university and start doing physical geography, usually it's not volcanic landforms. I mean, it's still interesting stuff, but it's much more likely to be, sand dunes or anyway. It's really geomorphology, which anyway. We get into all these little, subtleties of it. It's a bit like different subgenres of EDM, actually, now that I think about it. So, yeah, I remember when techno was new, and for a while there, we just called it techno, And then, but then it started to split. We had breakbeat and jungle, and then drum and bass came along. I'm dating myself, I know. And then, but now, there's all these different subgenres of drum and bass and other things. I mean, I remember trying to figure out what the difference between house and garage was in about 1991, and it turned out it's BPM. So more than 120 BPM, it's house, and less than 120, it's garage. Anyway, but otherwise sounds the same. Like, so yeah, we have the same thing, and and sometimes this is very much to our detriment because it becomes a form of passive gatekeeping when, if we're using words that are not in the common vocabulary, and until you're actually doing it, you might I have no idea what the difference is between these slightly different flavors of geology or environmental science. Anyway, so when I'm talking to if I go to an academic department and give a talk, then I usually describe myself as a miscellaneous petrologist, or sometimes an experimental petrologist. So the reason I say miscellaneous is because usually if you say petrologist, it's igneous or sedimentary or metamorphic, because those are the three main rock types. And when we teach rocks, there's usually a course in igneous and metamorphic, and a course in sedimentary. And the sedimentary is often combined with stratigraphy, how different rocks get layered and so on in sedimentary sequences. Anyway, so I'm pretty comfortable with all three. I used to do much more metamorphic. Now I do mostly igneous, but sedimentary rocks are fine too as well. And I also do weird things with rocks that most other people don't do. The heating up, the melting, measuring the physical properties, and so on. But petrology, I think, is my core expertise, I guess. And the reason that sometimes I'll present myself as a volcanologist, but I'll always hopefully clarify that I do a very specific kind of volcanology. Actually, most volcanologists do, because volcanology includes geophysics, geochemistry. It includes looking at the formation of lava, how it gets up to the surface, whether it comes out as explodes and forms ash, or whether it oozes out as flows. But you can study that with geophysics. You can study it with gas geochemistry. You can, all these different things. There are also important cultural aspects to volcanology. Oral tradition. In the last decade or so, people have actually been adding a lot to our understanding of the past eruptions of some volcanoes through studying oral tradition in the southwest US and elsewhere around the world. So in many ways, it's like planetary science, actually, in that you have a whole bunch of people with very different disciplinary expertise coming together to work on a specific, not one problem, but a specific set of problems. In planetary science, it's how do other planets that aren't Earth work? In volcanology, it's generally around how can we figure out what happened in the past, and how can that help us to again, not predict, but forecast roughly what we might expect to happen in the future and over what time scale. And so again, planetary science, I mean, I now go to planetary science conferences, I publish in planetary science journals. I think at some point when you've published, several papers in a particular field, I guess you're now part of the field. So I feel that with both volcanology and planetary science. But yeah, my training is hiking around the Himalaya, doing a lot of metamorphic metrology, some igneous geochemistry, some geochronology, argon dating. I had actually had friends who did both planetary geology and volcanology when I was in grad school, and we hardly ever talked about what we each did because they didn't want to know about isotope ratios, and for some reason I didn't really ask them very much about volcanoes, which is just bizarre to me in retrospect, because I wish I'd learned a lot more at the time, but I was busy thinking about the Himalaya. Anyway, so, but I mean, I always think the core of what I do is physics and chemistry applied to geology. So, that's when I'm recruiting, especially graduate students, I'm not worried if they didn't get a high score in paleontology, but I am worried if they didn't get a good score in, Chem 2, or ideally they'd have PChem. Like most of what I do is actually covered in PChem. Very differently, I've discovered as well. This is another fascinating thing. I used to teach a geochemistry class, and the students that took it would typically also be enrolled in Gen Chem 2 in the same semester. And it would be about 2/3 to 3/4 of the way through the semester, and you would see this light suddenly, dawn, and they go, "Oh, we're doing this in Chem 2 right now." I'm like, "Yes, we've been doing pretty much the same all semester. We just use different words and we talk about it differently, and the examples are very different. But, thermodynamics is thermodynamics, and redox reactions are, it's all it's all the same. It's just like the mental framework for it is so different." So.
Yeah, there's a couple things I could say to that. I think firstly, I completely agree with your point on or all of your points when it comes to like naming and semantics, and it almost like, I think science might be like unintentionally misleading people into thinking that it's not as specialized as it is, or maybe not. I don't want to make any general assumptions, but and it might be just ignorance on my part, but going into college and then starting to get involved in research, I had no idea at all how specialized things were. And so I remember telling people when I was in high school, it's like, "Oh yeah, I want to do geology. I think I might want to be a volcanologist." Like, but I had no idea what that really meant. It was like, if you want to be a scientist that studies volcanology, okay, what kind of volcanology do you want to study? Do you want to use chemistry to study it? Do you want to use physics? Do you want to use computer modeling? Do you want to go out in the field? What aspect of do you want to model magma flow? Do you want to do pyroclastic flow? Do you want to do, atmospheric chemistry? Like, there's so many different subsects of one certain science. It's like telling somebody that you're a scientist. It's like, well, what does that mean? Like, what do you study?
Yeah.
Oh,
Yeah.
yeah. But for like the general public, or someone that, just doesn't have the domain expertise to even like start to decipher all the jargon that we use. I think a little bit too much jargon in geology, but that's a separate conversation.
Right. I mean, there certainly is, and I always think that petrology in particular, because we have all these rock names. Mineral names is one thing. Different minerals have to have different names. The rock names, some of that is, I mean, we do it because it's a useful shorthand, but it's a useful shorthand if you're fluent in it. And until you're fluent in it, it makes everything opaque and incomprehensible. And so now I don't think that that's unique to petrology or even geology. You know, if you look at journals like Science and Nature that are supposed to be, articles there are supposed to be accessible to people from a wide range of backgrounds, try reading a paper about, brain cancer in mice, and, I can't make it past the second sentence. I have no idea what they're talking about. Like, these are all new words to me. Um, so, but I guess if I wanted to work in that field, I would have learned the vocabulary. But so and to some extent, I mean that's true. That's true in many aspects of life. I mean even just the slang that people develop and pick up. My kids are both Gen Z, so I can get them to translate things for me. Usually it's understanding a meme or something, but you know if there's a meme that a certain group of people share and understand what it means, and then nobody else does, it's not that different to there being a particular word that a group of people share that other people don't understand. So I don't know. I think it's a thing that people do. I mean, as long as hopefully we're not doing it intentionally to be kind of gatekeeping knowledge, because that's just stupid and counterproductive. I mean, I hate the idea that people go to college to get a degree, meaning that they have learned finally how to use the words of geology. All right, that's necessary, but it's not sufficient to be a geologist, right? I mean, yeah, you do need to learn some of the words along the way, but it's much more important to understand like the key ideas and processes and so on. But yeah, and that's where effective science communication comes in, which you know I certainly I try. Occasionally, I catch myself. I'm yeah. I'd suddenly start you know talking to some school group that's visiting the lab, and I just kind of forget, and I start using regolith and liquidus and solidus and the glass transition, and like have to like okay slap myself and like okay no, this is because the fundamental ideas are quite straightforward, and uh, again I ought to be able to communicate that just fine without slipping into jargon. So
Yeah, well, I mean, for what I hear so far, it seems like you're doing a great job if you take the time to talk to people in elementary school and things like that. I've met a lot of academics who don't even really bother, and their language is what they're going to speak, and they don't really like it's either learn their language or don't talk to them at all. Um,
yeah, and I
which
think
seems, yeah,
maybe part of that is like I guess UTSA is not a land grant institution, but it has a similar kind of mission, I think. And Mizzou and then Illinois, where I was before that, were all land grant universities. And of course, from the UK, where my education was funded by the government. Um, and I've always felt that. I mean, first of all, I think geology is great, and I wish everybody could appreciate geology a bit more. Secondly, geology actually is really important if you're thinking about large scale geopolitical issues, especially things that involve timescales longer than one electoral cycle. So things like climate change. Um, and water resources, energy resources. These are all big picture things that essentially all come down to geoscience. And if everyone were a little more literate in geoscience, that might lead to a little more realistic thinking about some of these problems that we all face, instead of just continually kicking the can down the road and assuming everything will be okay. Um, yeah, but also I just feel, I'm a state employee, and I've always valued teaching and research together. I mean, some people are, you know, perhaps really really good at one, really enjoy one, and maybe don't enjoy the other. It doesn't even matter whether they're good at it or not. If they don't enjoy it, they're probably not gonna do it so much. Anyway, I guess I like both, so that's good. I guess that means I'm more or less in the right job. Um,
Hmm.
so
Yeah. I want to loop back a little bit to the African lava flows that you were talking about.
oh,
I forgot the
Naragongo,
exact
yeah.
name that you used. Yeah. Um, and I didn't I wanted to flow with the conversation, but I also want to emphasize like how wild those are for anyone who thinks of lava as some kind of like slow moving, uh, like honey looking like flow of this like orange red hot liquid. It's like the what you see in Africa because they showed us this in my oh man, it was like my earth materials class like a
Hmm.
year ago. They showed the lava spewing out and it was like it had a viscosity that it looked like water. Like it looked like muddy water that was
Was
spewing
this
out, but it's like
Yeah, was that a video of Oldonyo Lengai in Tanzania?
I can't remember.
So there is so
Uh,
that volcano in the East African Rift, is that actually erupts carbonatite, which is a
okay.
very odd lava that is essentially sodium carbonate. So it's hot, but it's not as hot as regular silicate lava, but it's amazingly fluid. And yes, its viscosity is much closer to that of water. It's a little higher, but it's more like water than it is like regular lava. Um, I suspect if it really looked more like water, that's probably a video from Aldonio Lengai because I've a place I would really like to go sometime. But yeah, I've seen the videos and that is yeah exceptionally fluid. Um, at at Nyragongo, one of the results of our measurements were actually that the Nyragongo lava, it's at the fluid end of what we expect for silicates, but it's not massively more fluid. So the main thing is that the main reason that it is so dangerous is that it's actually erupting from fissures very close to where people live. But there's also great examples of very fluid lava from Kilauea in 2018. Also, Cumbre Vieja on the island of La Palma in the Canaries in, I think that was 2021. Um, and in both cases, the lava, you can see it moving at about 10 meters per second, which, just for context, that means 100 meters in 10 seconds. Well, it's the Olympics right now, and the Olympic world record is 100 meters in just under 10 seconds. So this lava is traveling at, world champion sprinter speed. It's certainly going to beat me every time. So
Yeah.
now the good thing is it's in a channel, so as long as you're outside of the channel, you're probably okay. The bad news is occasionally you get overflows or breakouts, and so then it. But but yeah, so I mean, even on Hawaii, that's actually something we're working on a paper right now. Is to try to well, we've been doing some experiments where we've finally managed to measure the viscosity of lava with both bubbles and crystals in it simultaneously, which has generally been difficult to impossible to do in the past. Um, and anyway, it turns out that with bubbles in there as well, the viscosity is really low, much lower than we would have expected. And so that helps it to travel so quickly. And of course, this is near close to the vent. It's still very very hot. The main thing about such hot lava is it radiates a lot of heat and it does cool down fairly quickly. But Yeah.
Yeah, that's interesting. I always thought that like the reason that these like felsic eruptions are so explosive, like
Hmm.
Mount St. Helens
Yep.
or um, maybe like some kind of volcano in Alaska or something like that,
Yeah.
is because partly because there are there's gases in that. I guess when it's underground, it would be magma. There's gases in the magma,
Hmm.
and then that does something to raise the viscosity, so it takes, but like it's able to hold more and more potential energy as you put more and more stress on it. Is that right?
Approximately, yeah. So the main thing, what drives volcanic eruptions, is generally expanding gas bubbles. So most lava is, um, if you ignore the bubbles at least, most lava is pretty dense. So why does it rise up towards the surface? So usually at depth, the magma is going to be less dense than the surrounding rock, so it does tend to rise relative to that. But then, once it gets to the surface, what really drives it to come out of the ground, and in some cases to, go a long way in the air. Again, Kilauea on Hawaii in 1959, the Kilauea Iki eruption. There's video, like, old timey, it looks like ancient newsreel, but it's really cool video of this lava fountain just going up like half a mile into the air, just spraying like a fire hose. It's phenomenal. The eruption in Laki in Iceland in 1783 was, I think that was supposed to have gone, more like a full, certainly more than half a mile in the air. I forget the actual. I think it was close to a mile. It was ridiculous. Um,
Yeah.
so it's so what leads lava to come out at such a high speed? It's the gas bubbles that, as they rise towards the surface, they decompress and they expand. So the volume of the lava is actually expanding exponentially as it approaches the surface. So from ideal gas law, PV equals nRT. So as the pressure goes down, the volume goes up. Pressure at Earth's surface is 1 atmosphere. The pressure just a few meters below the Earth's surface is hundreds to thousands of atmospheres. So you get this very rapid expansion as it's approaching the surface, and that's what really drives it out. And then for the big explosive eruptions, Mount St. Helens, Pinatubo in 1991, and so on. That's when the lava is usually, the simple explanation is the lava is really sticky and the gas can't escape. And so the gas bubbles as it's getting towards the surface, the gas is still really pressured. It's If it can't expand, it's essentially still got the same pressure in it that it had at depth, except now the confining pressure on the lava is much less, especially when it gets to the surface. So you've got gas bubbles with a lot of pressure inside lava that is just at the atmosphere. Well, those bubbles eventually, um, they can't expand through viscous flow. They just expand by shattering the rock in the end. And that's when you get production of volcanic ash and pyroclastic density currents and so on. In practice, it's a little more complicated than that, and again, volcanologists have spent a lot of time trying to figure out, like there are questions like what is stronger, the crystal or the liquid? And you would think that that would be really easy to answer. There's also it also can be tricky because if I say what's stronger, does that mean what is more rigid or what can break more easily? Because it turns out that rigid things can break quite easily, and things that are less rigid are more able to flow and less likely to break. So it all becomes a little, it becomes much more complicated. Anyway, but yeah, the key thing, if you want to avoid an explosive volcanic eruption, you need to find a way of allowing the gas to escape. And so with fluid lava, that's easy because the bubbles can just escape from the fluid, just as bubbles escape from a can of soda or something. Although, as you know, if you get a big bottle of soda, especially if you get the sugary soda, not the diet, so it's got a higher viscosity, and you toss in a bunch of Mentos, uh, it's going to trigger a lot of degassing of that dissolved CO2, and it's going to spray in the air. Doesn't last very long, but it's all about how fast the gas wants to come out. So if you can find a way of just bleeding the gas off slowly, then you can be relatively safe. If you can't, the longer the gas stays in there, the closer it gets to the surface without being able to relieve that pressure, the more explosive the eruption is going to be. That's I'm not sure if that made sense, but that's basically how it works.
No, yeah, that made total sense. Is that why when you were explaining earlier how the introduction of gas bubbles into lava flows raises the viscosity and makes it therefore flow slower? But that is only the case because you're on the surface and there's not a huge pressure differential between, like, under being underground and then being under the atmosphere.
Yeah, so actually, right, once you're in a lava flow, and we're going to assume that, I mean, actually, I've worked with some lava flows that there's this one in Chile that I'm hoping to go back to soon, fingers crossed for funding, but anyway, the Chao Day site, it's a 26 cubic kilometer. It's described as a coulée, which is French for flow, but a coulée is what happens when you get a big blob of lava that, if it were on a horizontal surface, it would just spread out and form a dome. But it actually erupts on a slope, so it kind of splurges down the slope, but it doesn't really flow in the way that, like a Hawaiian river of fire kind of lava flow. It's more like a big pile of mud that just kind of oozes and gets longer. Anyway, this thing, it's 400 meters thick. It's absolutely amazing. So the pressure at the base of that is actually quite considerable, and you could have quite a lot of dissolved water that would be happily dissolved under that pressure compared to the top of the flow. But that's a very unusual circumstance. For a thinner lava flow, yeah, then there's not much pressure gradient from the surface to the base. The bubbles are generally not massively overpressured, so they're not trying to explode, but they're just there as bubbles. And then the question is, what do bubbles do to the viscosity of the lava flow? The first thing is, pretty much all lava flows, no, most lava flows contain some crystals. And just as you mix mud into water, that muddy water is harder to stir and more viscous than the mud-free water. The more crystal in the lava flow, generally, the more viscous it is, the slower it will flow. Bubbles are weird because they can go either way. If the bubbles are, generally, if they're small bubbles, they'll stay more spherical and they don't really deform much. Well, if they're essentially rigid, undeforming particles, then they're behaving much like crystals, and they actually increase the viscosity of the flow. And I remember this being very confusing to me the first time I learned about it, but one example is, what happens if you whip a bunch of air bubbles into cream? Does it get more or less viscous? And if you sat there trying to whip cream, you know that the more bubbles it has in there, the more viscous it is. So that's what happens if they're small spherical bubbles. Larger bubbles tend to deform more easily, and then they'll get very stretched out. And then these essentially form huge planes of weakness, of low resistance to flow, and you'll get a lot of shearing across those bubbles because internally the air in the bubble can deform much more easily than the silicate melt on the outside. And so they can really reduce the viscosity of the flow. So bubbles can go either way. And the next problem is, how do we know what they're doing in the lava flow, right? We can collect a sample of the lava and we can quench it. But in the time it takes us to cool it down and quench it so it's rigid, has that bubble had a chance to go from this long stretch thing and become more spherical? So the one thing we can be reasonably sure of is that the bubble isn't going to become more stretched while we're quenching it. If it's going to relax at all, it's going to relax towards being spherical to minimize its surface area. So when we look at lavas that are quenched from lava flows on Hawaii, for example, then a lot of those bubbles are actually quite stretched. And so that confirms that the bubbles in that flow, we don't know exactly how much they were deforming. They must have been at least as stretched as we see them once they're quenched and solidified. And so so it does actually make sense that these flows are relatively low viscosity. The interesting thing is that no, as far as we know, and we need to submit this paper sometime in the next few days. As far as we know, nobody's managed to do in situ experiments with lava with both bubbles and crystals in it. And what we find is that the combination of the two is still much more fluid than we would normally predict based on our existing models. And so this is an important thing to know. People have done analog experiments. I love playing with food, as you can probably tell from the whipped cream analogy and other things. So experiments with like corn syrup is the go-to substitute for basaltic lava. Of course, you can put air bubbles in it, but they tend to escape pretty quickly. So actually, people often will do something like baking soda and vinegar to, usually citric acid, but anyway, they'll make something to generate bubbles inside the syrup, and then for crystals we use things like sprinkles if we want elongate feldspar looking crystals, or poppy seeds, or anyway, there's all kinds of different literally experimental recipes that people have come up with over the years to do these analog experiments. I always prefer doing the high temperature experiments if I can. It's just they're really difficult and they go wrong quite a lot. So.
Yeah, that really reminds me of the way that a glacier will flow, especially when the bottom isn't melted, so the bottom is still frozen, and usually what happens is that there's a viscosity gradient through the thickness of the ice sheet or the glacier, and so the top will usually flow faster than the bottom. So the bottom will kind of be stuck to the bed, and then the top will kind of like there'll be like individual layers within the ice that are kind of sliding past each other. And it another thing that makes me draw the connection too is how there's different behavior, like you said, of lava flows at different pressures, and the pressure can mean a lot, especially when you're talking about hundreds of meters of something that is pretty dense. And subglacial volcanism has been something that I've always been interested in, especially in Antarctica. And I'm wondering if you have any thoughts of like how lava flows and eruptions might behave differently when you have 2.5 kilometers of ice on top of a volcano.
Yeah, so again, there are people much more qualified than me to talk about this, but because that's a whole niche subspecialty in itself, is the glacial volcanologists. But like a few simple things. So first of all, you get these fairly unique landforms called tuyas, so Tuya. And these are particularly well exposed in Iceland, where of course there's been a lot of subglacial volcanism, and the glaciers in many cases have subsequently melted. So we can actually see the shapes of the hills. So they tend to have very steep sides, very flat tops, and I enjoy thinking about glacier volcanism. I've never really worked on it, but mainly because of all the heat flow and the thermal budget is kind of interesting, because it takes a lot of energy to melt ice and then to heat water. And so you've got this race between heat coming out of the lava and heat going into melting the ice or heating the water, and then the outside of the lava is going to become rigid, whether it crystallizes or just forms glass. And then actually when it does form glass, it then tends to react with the water, and you get this stuff called palagonite. Um, it's kind of hydrated mess of clay minerals and so on. Anyway, yeah, it's a really messy, complicated thing. And yeah, uh, maybe I've shied away from it because I think it might be too complicated for me. I don't know. But also something I'd like to do experimentally sometime, but that might require a bit of investment in an appropriate experimental facility. There was an example a few years ago. There's a at the University of Syracuse, Syracuse University, whatever its official name is, they have a big lava melting apparatus there, just a big cauldron basically, and then they pour it out onto various substrates. And there was an example a few years ago where they actually poured it out in winter, so it was pouring out onto ice and snow. And that was really interesting because, you might think that, well, the lava's hot, it's just going to, melt and go straight down. Um, and that's actually not what happens. It goes across the surface. It is melting the upper surface of the ice. But then that vaporizes, and then that forms these big bubbles. So the flow is just doing this big loopy thing,
Hmm.
with all of this water vapor, but it's not really able to just melt down through the ice. And the really nice thing about this, the guy that led that, Ben Edwards, had previously studied this eruption at Tolbachik in the Kamchatka Peninsula, where the lava flow had erupted, in the this is the peninsula that dangles off the east end of Russia. It's pretty cold there, especially in winter. There'd been this eruption, and yeah, basaltic lava had flowed out over this snow and ice, and essentially the same thing. They saw it in the real world, and then were able to simulate it. And of course, the nice thing about doing it in a controlled environment is you can have things set up to measure and see what the temperature gradients are, and have an infrared camera and so on. So anyway, it's pretty fascinating, and likely did occur on Mars, by the way. So there's lots of evidence for past glaciation on Mars. So relevant not to planetary as well as terrestrial volcanology, but yeah, it's fun things to think
Yeah.
about.
The reason I ask is because that's the primary focus of my research has been anomalous subglacial or anomalous geothermal flux beneath the Western Arctic ice sheet, which
Mm,
is a fancy way to say subglacial volcanism in Antarctica. It's
right.
just
Yeah.
that like you said, it's very complicated and it kind of stirs up the field. So you want to be careful with the semantics, especially when it's so poorly constrained.
Yeah.
But from a lot of the stuff that I've read so far, and a little bit of the work that I've done, I mean, ice is less dense than water, so the amount of overburden pressure is going to be similar to any eruption at the bottom of the ocean.
Hmm.
The weird thing is that you have an extra phase transition. So, if you have a bottom eruption at the bottom of the ocean, you're going to boil that water, and it's going to, want to turn into gas, or it's going to want to heat up and then rise due to convection. But you can't really like convect ice. I mean, you can on Europa, but not really in Antarctica.
Yeah.
And so you have, this subglacial eruption. It's under a lot of pressure, and then you start to form these pillow lavas that
Hmm.
kind of branch out, and then that'll melt a lot of the ice. So in Iceland, usually the ice is shallow enough to where the eruption breaches the surface, and then you end up with this kind of lake. And like you said, you develop these really steep walls because all the eruption is starting to take the form of this almost like ice mold around it.
Hmm. Yep.
There's really good examples of this in Oregon.
Hmm.
There's this place called Hog Rock, and so the Laurentide ice sheet was this huge ice sheet, covered the entirety of Canada, like 20,000, 30,000, yeah, like 20,000 years ago, and it covered Oregon as well. And so you had a ton of ice, but it was shallow enough in that area to where the eruption probably breached the surface and formed this like water body. In Antarctica, it's way too thick to breach the surface.
Mm-hmm.
And so everything's contained under the ice. And so constraining what that would look like is really difficult, especially when we don't have any actual observations of what that looks like, because not only the only way that we can look at it is through radar or through seismic data,
Yep.
but it, like, as soon as the eruption stops, then everything starts to kind of freeze again, and then as the ice flows past, it'll erode the bottom, and it just completely wipes away the volcano. So whatever edifice you formed from that pillow lavas and eruptive material just gets wiped away in a short amount of time on geologic timescales.
Right.
So probably a couple thousand years, couple million years. And there's a lot of really cool examples of how that integrates with like this whole sub-ice water network, which is starting to leave my realm of limited expertise as it is, but it's really cool stuff. It is really interesting. And then ice thermodynamics is something that's really cool in regard to Europa as well, with like I mentioned, this convecting ice and these cryolavas, as you call them, different brines at different pressures and temperatures, doing different phase transitions and freezing and all of that stuff. It's wild to think about.
Yeah.
So on the subject of cryolavas, I guess, could you define what that is for me?
Sure, I'll give my definition. So cryolava, of course, means cold lava, which sounds weird, but so as you know, on Europa, which is an ocean world but has a crust of mostly water ice forming its surface. So on Earth, if we partially melt the Earth's crust, then we will get silicate lava. If we partially melt the Earth's mantle, we'll get silicate lava. It'll be basalt. If we partially melt the crust, we'll get something more silica-rich, like a rhyolite. And then it erupts at the surface, and it's cold enough at the surface that lava then solidifies. So this is why it's called cryovolcanism, and not like a geyser or something like that on Europa. The crust is made of H2O ice. If you partially melt that, you will get a brine, which just means water with a bit of salt in it. And then when that erupts at the surface is cold enough that it will then very quickly freeze, probably after flowing some distance. So, and then Europa's mantle, I guess, really is its ocean. So it's there's a substantial. We're not sure exactly how thick it is and how thick the ice layer of the crust is either, but we know that there's a big salty ocean down there, and that's essentially Europa's mantle. So if bits of that make their way to the surface, it's probably saltier than anything that would happen from melting the crust. Anyway, so right, cryolava, it's basically aqueous solutions that erupts on a body where that's going to freeze and solidify after reaching the surface. So yeah, we did some studies on it, and there are kind of two different approaches to cryovolcanism, and ours was definitely the low viscosity end. So there's probably cryovolcanic activity, or has been, out even on Pluto and its moon Charon, and certainly on Europa, the spectacular surface textures of Europa, where you can see all these ridge terrains that have clearly broken up into fault blocks and slid past each other and rotated and so on. Some of these are attributed to, as you mentioned, convection. So that would be solid state convection within the ice of the crust. Of course, solid state convection happens in the Earth's mantle as well. So initially, it's a bit of a weird concept, but it's quite well accepted in geology. The Earth's mantle, though it's solid rock, it can, because it's very hot, it can flow on geological timescales with effective viscosities that are billions or trillions of times higher even than silicate lava. All right, so we can have this kind of convection within the icy crust. There's probably solid nitrogen glaciers on Pluto, and I forget what else there is out there because that always just blows my mind. But it's so low temperature that it's way beyond anything I can do in my lab, so I kind of space out sometimes with that stuff. Anyway, so there's that kind of solid convection, and then what we've been studying is literally just basically eruptions of salt water on the surface of Europa. And the reason we were looking at that is, there are missions going to Europa, Europa Clipper, of course, going very soon. And the reason Europa is such a high priority target is because it has this subsurface ocean, which potentially could harbor life because there's a lot of liquid water there. There's potentially even, there's probably not like mid-ocean ridges like we have on Earth, but there's potentially hydrothermal vents at the bottom of the seafloor. Although there were a bunch of talks at the Lunar and Planetary Science conference this year suggesting that everybody's models make it look like there's probably no hydrothermal vents and probably not much chance for life either. But anyway, but hey, those are just models. We won't know till we go there and look, right? What we'd like to do, and what gets the engineers excited, is the possibility of some autonomous drilling machine that we fly to Europa and drills through the potentially 30 kilometers of ice, we don't really know exactly, and gets a sample of the ocean of Europa to find out if it has little green bacteria in it. They don't have to be green because there's probably no light down there. It doesn't have to be chlorophyll. Anyway, but an easier way, which requires slightly less heroic feats of engineering, would be to find a place at the surface of Europa where the seawater had come to the surface, rather than drilling down to the seawater. And so if we could identify what cryolava flows, which would essentially, if when these plates are moving around, and they're very small fractured plates, but as they move around, there's likely to be some transtension, meaning they slide past each other, but also slightly apart from each other. That would then allow potentially seawater to rise up from below and squirt out through that crack. So what we were looking at is, what would the viscosity of that material look like? How fast could it flow? How far would it get before it froze? And one thing that was really cool, actually, I thought it was exciting, was the main problem with cryolava on Europa. Problem's the wrong word. The main process that removes heat from it is in fact sublimation. So it basically, some combination of boiling, but probably mostly the outer surface of the flow would freeze solid, but then that goes directly from solid to gas and just like evaporates. So one question there is, how much of a flow would be left afterwards? I mean, that's only an issue while it's hot, of course. Once it's cooled down, it's not going to evaporate. Anyway, so we were trying to figure out, how fast these flows could move, how far they might get before they solidified, giving some guess at what they might possibly look like so that we could try to identify them. Anyway, but that's a lot of times when people talk about cryolava, they're really talking about the solid state convection, like the nitrogen glaciers on Pluto or ice convection on Europa. But there is this other, at least we hope that there's this other low viscosity end member as well.
Yeah. So many directions I could take from that. so many questions I could ask, but I feel like I'm eating into your time a little bit. We're like 26 minutes over. Um,
Yeah, I should probably. I'm sure I have a lot of emails at this point, especially given the things on my to-do list for today. But
yeah, but super fun conversation. I really, really enjoyed all your explanations. They were all really easy to follow, especially for complex topics, which is really impressive. And it's a
oh,
skill
thank you.
that I'm still trying to gain myself. And yeah, I really appreciate you taking the time to come on the show and just like come talk about the research that you do. I mean, it's really cool stuff.
Yeah, well, it's been a fun conversation. Yeah, I've been very lucky to get to do what I do, and I love talking to people about it. So
Yeah. Yeah. Well,
good.
awesome. Thank you.